Welcome. In this lecture, I'll introduce electric machines, devices which can convert electrical power into mechanical work. I will talk about how they are constructed to generate torque and the principles underlying their operation. As I've mentioned before, electric machines are capable of producing rotational force more or less directly from electric power, which makes for efficient and reliable electric drives. From observation, we know that a wire carrying a current in a magnetic field experiences a force proportional to the magnitude of the current and the field strength. This physical phenomenon is explained in detail by Faraday's law, which, for the geometry of an electric machine, can reasonably be simplified to the expression shown here, IL cross B, where I denotes the current carried by the wire, B is the magnetic field, and L is the length of the wire. As current flows from the battery through the wire loop, a force is induced on the sections of the wire perpendicular to the magnetic field. The direction of the induced force depends on the direction of the current and the B field, which means that the force on the two straight sections is equal and in opposite directions. This creates a rotational force in the coil. By including more and more loops in the rotating coil and by increasing the current and field strength, we can make machines which produce appreciable torque. An unavoidable and necessary consequence of the motion of the coil rotation, as shown here, is a generated voltage potential, the so-called electromotive force, or EMF, which opposes the flow of the current supplied by the battery. This is how an electric machine operates as a generator, allowing us to take advantage of this EMF to recover electrical energy from mechanical motion. Here we zoom in a little bit and look at the forces on the loop in more detail. The magnetic field B is generated by permanent magnets, with field lines originating at the North Pole and terminating at the South Magnetic Pole. You can find the direction of the force in the wire perpendicular to B by applying the familiar right-hand rule for a cross product. By pointing the index finger of your right hand in the direction of the current and orienting your middle finger in the direction of the B field, your thumb will indicate the direction of the force. Most electric machines contain the same basic components for exploiting Faraday's law. There's a rotor, a central armature which carries current and rotates. There's a stator, a stationary component that sets up the B field. Then a commutator, or a control device, which ensures that the current flows with the right direction and timing through the coils. And low friction bearings, which allow the rotor to spin and produce torque. This arrangement can be varied in a few ways for different applications, but the underlying principles of operation are very similar. In general, electric machine designs fall into a few important categories. Simple brushed DC machines, closely corresponding to the model we've covered here, induction machines, and brushless permanent magnet machines. Here is an image of a disassembled brushed DC machine showing the rotor windings, housing and stator, and the commutator and brushes in the top right. The cutaway pictured here is an induction machine. In this design, the rotor is short-circuited and a current is induced in the rotor coils by induction using a time-varying stator field. This arrangement eliminates the need for brushes, which can be a weak point in the design of some electric machines. Here's another view of the same induction machine design, but with the rotor removed for viewing. In this slide, we can see the anatomy of a brushless DC machine. On the left, we can see that the stator and the rotor functions are reversed. The stator contains windings which carry current, and the inner rotor is constructed with strong permanent magnets to generate the required magnetic field. By synchronously energizing the poles A, B, and C, shown on the right, we can produce torque which acts on the armature. Machines like this can be constructed with many poles for smooth and continuous torque. Again, the purpose of the electric drivetrain is to supply torque to the load in response to driving conditions and user demands. In addition to the motor limitations, efficiencies of the supply and conversion electronics have to be included when thinking about the drivetrain function. Here we see a typical power response curve for an electric machine. At low RPM, power output grows linearly with increasing speed. As we reach higher and higher speeds, the generated back EMF becomes appreciable and power output tops out. In the plot shown here, we see an ideal torque versus speed diagram for an electric machine. As before in the power diagram, two curves are shown, one available for intermittent use and one that permits continuous operation, determined by physical and supply limits of the electric machine assembly. Directly from 0 RPMs, an appreciable amount of torque is available, but it's limited by the max sustainable machine current for the electric machine in the continuous case and by the max of the current supply in the transient case. Eventually, as the speed increases, the supplied torque is reduced, limited by the maximum battery power and the maximum voltage, which must work against the EMF induced by the armature motion. In this figure, we see the same torque versus RPM diagram plotted for a real brushless DC motor used in an automotive drivetrain. In addition, a heat map showing the energy conversion efficiency of the electric machine assembly for different torque and RPM values is plotted on the same axes. Note that efficiency is high over the entire range, but noticeably lower for extremely low and high RPM values. When we model electric machines using QSS and MATLAB Simulink, a map like the one pictured here ultimately governs the response of the model and helps us make intelligent choices about vehicle designs. If we open up Simulink, we can find the electric machine building blocks in the energy converter section of the QSS toolbox. As before, our quasi-stationary simulation processes driving demand outcomes to yield power consumption. In both the motor and the generator models, gear ratio and torque inputs are used to determine supplied power needs. In the generator model, input torque interacts with an efficiency mapping to yield a power generation. In the electric motor model, desired torque and gear details are combined with the motor efficiency map to compute the consumed power. Using these Simulink model blocks is fairly straightforward, but take special care to check the max electric machine power demand and the maximum machine speed are not exceeded. With the basic principles covered here, you should be ready to use QSS to explore some of the electric powertrain design space for road vehicles. Thanks for listening and have a great day.